Welcome to dynamic programming, and the problem today that I'm going to work on is traveling salesman, and the way I'm going to show or solve the problem is by using Jupyter Notebook. Now the way I have set it up before I dive into the problem, I hope everybody understands what the traveling salesman problem is. We have a salesman that's trying to travel across a bunch of cities. In my case, I'm assuming the cities are 1, 2, 3, and 4. Keep the problem simple. And I'm given a distance matrix between any city and any city. In this case, distance from 1 to 1 is 0, 1 to 2 is given, and so on. And so I have been given this adjacency matrix of distances. And then given these distances, the problem is really if I want to start at 1 and create a tour ending at 1 and visiting every other site in this set only one time, what is the minimum cost of such a tour? And so this is the classic traveling salesman problem that most of you studying dynamic programming probably have heard about it. I want to motivate the solution in the following manner. So if you look at this problem, I first try to figure out what is the relative complexity of solving it the brute force way, which is the factorial. So if you could find all the possible solutions of n sites and find which one's the smallest, that would give you the solution to this problem, but that would take factorial time. And so if you take and plot factorial, which is plotted in red here, red dots, so you can see that the curve basically just explodes right here. It just goes through the roof right here, while the other curve, if we solve it using dynamic programming, the answer turns out to be 2 to the power n times n squared. And if I plot that function, it also is pretty bad because it's an exponential function here. It's 2 to the power n. It explodes as well, but it explodes much later. And so you have the benefit of being able to use dynamic programming all the way up to a set of nodes here, which is, you can see almost 800, 900 nodes, which is fairly decent. So being able to use dynamic programming gives you the ability then to execute this task in a reasonable manner for quite a lot of nodes, and eventually it gets very expensive. So with that motivation, let's look at, I'm going to skip over some of the installations, and you can skip over them as well if you have them already installed, and let's just dive into the code. So here in this code, as I'd already talked to you, the problem is set up by a distance matrix, which is really an adjacency matrix. And another thing I set up is predecessors. So predecessors is when you find the minimum path to a certain node by arriving through a set in the middle, what is the predecessor? And in the beginning, I say 1000 is kind of like infinity for me. And so all of them are 1000, and the smallest path going through almost nothing. There's no set in the middle. If there was empty set in the middle, then reaching a given node from 1 would be 1. So this is assuming everything is fully connected. So 2 can arriving using no other nodes, the shortest path would be through 1, and so on. And so we want to fill this out. So we have predecessors, and we have cost vector, and the cost vector we'll describe in a little bit. That is also an interesting thing that kind of gives us the answer. So basically the recurrence here is, if you look through any textbook or Wikipedia implementation, the cost is described in terms of a set S and a destination J. So if you're arriving at, let's just say you arrive at a point, you go through a set of nodes, and obviously 1 is the beginning, right? You start at 1, then you go through some number of nodes, x, 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 x. There's some number of nodes in the middle, and then you arrive at some node which is, let's say, j. So the problem is set up by saying that the optimal recursion is by understanding that the problem is broken down this way, that there is a destination j, and there is some set in the middle which we call S here, and the beginning is always 1, always start at 1. So if you do that, then this is minimization problem over assuming j remains, but any node in the middle, this s, we pull out one node at a time and say the set s now becomes s minus some I, and when you take that node I out, the cost then becomes the cost of the set reduced set with I and the distance dij. And so then you minimize over all these distances, and that becomes the new minimum. And why is this a dynamic programming problem? Because I could always start with small sets, like empty set is in the beginning, and then I can grow my solution from there. A set of one node, a set of two nodes, a set of three nodes, and so on and so on. And I can easily compute this matrix. Now, obviously, representing this set is not such a trivial thing. So I show you here, the way I try to do is I form a hash table, and the hash table is basically defined as the cost I tabulate using a set, which is described here. An empty set is just a dot, and a destination j, and destination j, and so I'm basically implementing this key here as key subset is a subset followed by destination. So initially I know that if the set is empty, the cost is basically a direct cost between 1 is infinite, because you can never go from 1 to 1. I could yeah, so the cost of reaching 1 is really, and I could make it 0 as well, but I don't think it matters. Cost of 1 to 2 is really the distance between 1 and 2, and I say 1 1 because that's the way the the Python works, is that this is column is 0, this is 1 2 3. So basically it's a direct distance. So the cost initially is just a direct distance when the subset is empty, and it's easy and pretty obvious for even humans to figure this out. Now when I say humans, I don't mean in a derogatory fashion. I mean, like, computers will then go on to compute a lot of data, but even us humans can see that if the set was empty, then the distance is straightforward, and the minimum distance is just the distance, straight line distance between the two cities. So now what we do is to run this algorithm. Now that we have the basic cost structure set up with this key format, now we can take any subset and then we can represent that subset in the form of this key subset format, which is subset and the nodes dot, if you have two nodes, let's say 1 and 2 in this subset, I could say 1 dot 2 dot, and that represents that middle portion, and then the destination followed by the underscore followed by destination. So now in our case, 1 is never put as a superset, so the remaining superset is really 2 3 4 in this simple example. And so I create two functions. First function is basically, given a subset, return me all subsets of a given length, right? So if I give you 2 3 4 and ask a subset of length 1, it's going to give me a subset 2, subset 3, subset 4. And if I say length 2, then it'll give me 2 3 3 4 2 4. So this is what this function does. And then return minus, meaning if I want to pull an element out of, because remember that when we did this, to reach j, we pull one element out, and then remaining subset becomes the next lower level or subproblem, and that's how we could optimize. So I create another function which is given a list. I could pull an element out, and I can return a shortened list, which is simple enough. And make key is another interesting function. So given a list and a destination, I basically create the hash key, which is I take all the nodes in the set. I do like node 1 dot node 2 dot node 3, and in the end a dot, and then a destination, right? So this is easy to understand. Now here's the meat of the solution, which is the populate min. And populate min will basically take a list, which is a super list, and then given a size, so it's operating on a certain size, and a destination. So this will then compute the minimum and will also compute the predecessor list for that size. Now remember that for every given size of the set, there is a predecessor and there is a minimum. So so we start at empty set of size 0, and then we basically, as dynamic programming evolves, we go through sets of size 1, sets of size 2, 3, so on for any given destination. So that's how this problem operates. And so you can see that given a set, which was, let's say, a large set, I first create all possible subsets of that size, and given that size, I can then operate on every possible subset with that destination, and then I will then remove that destination from that size S, and then I will make a key with that given set and the destination, and then followed by I will pull out one element. And so what this really means is that if I'm going from some set, let's say S, to dest, and I'm going to comment this so that it's obviously not interrupting my program flow. So what happens is that what I'm doing here is that first of all, given a size, I compute all possible sets. So I could have, in this case, the loop above is basically I could have S1, I could have S2, I could have S3 as my S. So first I compute all possible sets for a given destination, and that's this loop above. And then in this loop, what I will do is that I will pull out, given a set, let's say S1, now I will sequentially pull out every element, let's call it P. So I'll pull out every element P from this S one at a time and compute the distance of, let's say, the remainder of the set. So S1 minus P, going through that to let's say P going to dest, right? And I will take, I'm sorry, this should be P here. And so all the possible solutions of this is what this loop will minimize over, right? And so I will, and actually I minimize over all possible subsets as well. So given that, I will minimize this calculation, and the calculation is this cost and the distance and the total cost. So if the total cost is less than the min, I store the minimum cost of arriving at this point, and then I also compute the predecessor. So once I find the minimum cost of computation, then I store that in my predecessor as which element was it that I had pulled out here before the destination. So I store which element it was, and the set was obviously reduced. And the nice thing is that when you are trying to solve for S1, if you remove one element from S1, the size shrinks by 1. And so voila, that's the dynamic programming iteration, because a solution at size X is depending on solution of size X minus 1 right here, because I pulled out this P. So this is the previous stage, and it's already pre-computed for me. So all these pre-exist, and therefore you can see that I can compute all this. I can compute the cost vectors and the predecessor vectors. And then obviously if the length, if this S, and what is S here? S is, if the size is really 0, if there is nothing in there, then the cost basically is returned, because it's not reachable, right? If the cost is if there is no elements in the middle, then the cost is, I'm sorry, what it means is that if the length is not 0, because if it's 0, I had already predetermined, I've predefined that value, right? So for set size 0, which is only an empty set, this is already predefined. So when I run over this iteration, I'm only populating the ones where set of size non-zero, which means at least there is one element in that set in the middle, right? When the iteration starts, this set has to have some node inside it. If the set size is 0, then there is no solution, and I already know that's a direct path from node 1 to that node. So that is it. And now I start my final main loop, and in the main loop I start by populating over all the lengths. So I start with length of 1 and go up to length of SL, and I go plus 1 just for the sake of, because I subtract 1 from it in the above loop. So I am essentially populating for that superset that we talked about, which is all the nodes And if you have 100 nodes, put the 100 nodes list here. And then the I is, you start with one node, and I start with one, not 0. So I start with one node and so on till length of SL plus 1. And then it's K. And what is K? So K is, because the destination could be any node, right? So if the destination could be one of the nodes in this SL, then I could basically pull that out and iterate over the min. And populate min will, given that set size and given a destination, it'll find and populate the min vector of the cost. It'll update the cost vector and the predecessor vector. And if you start from, so if you start this this calculation from size 1, then you get, when you go to size 2 will then use data that's computed before, and size 3 will use data computed from size 2, and so on and so on. So that's how the recursion actually works in this case. And when you compute for size I minus 1 is already done for you. So that's why this iteration works. And then finally, once you have gone through all the set sizes, arriving at some node K, then you have to go back to 1, because the whole thing is a tour, right? So we have to finally compute this last, given all possible nodes, and given that this cost vector is working for the some destination node of all the set nodes, we have to then go back to 1. So this final stage of computation is given the set SL minus, so you always take that node, take it out, and that's your set S. So we figure out that, we make a key for it, and then we extract the cost and add the distance of going from K. So any given node back to 1, and which in this case is in our reference point is 0. So if we take the cost computed above in the previous function and add the distance going back to 0, and then take a min over that gives you the total minimum of the tour, which is going from 1 to a set to some destination back to 1. And so this is the final answer. And then at that point we can print the minimum cost is from the node, which is, we can keep track of which node was the minimum and what the total cost was. And then we can also print the predecessor tree, and using the predecessor tree we can basically walk back and find the actual minimum tour. So with that, if you just run this, I do shift enter, and that should update it, and it tells me that the minimum cost is 46 for the tour, right, going from 1 to 1. And if you back up, it came from 2, and if you back from 2 came from 3, and then 3 came from 4, and then 4 came from 1. So the tour was 1 4 3 2, 1 4 3 2, and back to 1, 1 4 3 2, and back to 1. And you can see that if you follow this predecessor vector tells you that given a node 2, if you want to find, if you are given a set of size 3, because when you take 2 out, in this case if you take 2 out, we know that 1 is out and 2 is out, so only nodes remaining are 3 and 4. So the set of size 2, right, so the set of size 2, 0 1 2 for 2 is 3. So this is the predecessor. And so that's it, guys. So using this Jupyter notebook, you can plug away. So what you can do is you can come here and you can change this distance vector and the predecessor vector, and you can plug in any problem here. And if you do that, then this program will basically, and obviously you have to come here and update a couple more things here. I could probably make this more generic, but you have to come and update everything up to this point. And then this is where the program starts. So above this line is all the config, so you have to come and update the config and update. If you change your problem, you have to basically set your nodes, set the predecessors. It's probably simple, but then the keys have to be also updated, and the starting list or the super list has to be updated, not including one but all other nodes. If you do that, I'm pretty sure this will provide you the answer to the shortest tour problem of traveling salesman. So there you have it, guys. This is the end of this presentation. Hope you enjoyed it. If you liked the presentation, I would really want you to download this Jupyter notebook, give it a try, and see if you can plug away at your problems, and then try to understand it and see if it makes sense. If you have questions, do leave me a comment, and if you liked it, give me a thumbs up, and do subscribe and hit the bell button, so in case I come out with new videos you have notifications. And I really thank you guys for spending the time today with us, or whenever in future when you're looking at it. But yeah, I really thank you, and hope to see you in another video. Bye bye.